Okay, can we start? Okay. Welcome. I'm Andrej Bauer. I would like to thank Frederick for organizing the school and everything else in the EuroProofNet. I'm sure you will think twice before running another one. But it's been a great contribution to the community. So let me get on with the lectures. So I'm going to speak about a little bit about how to implement type theory. And we're going to also do a little bit of programming language, like we take ideas from programming languages and try to apply them so that we see how these things fit together. But today, we are not going to do any coding, because for something like a programming language or a type theory, it really helps if you have a good idea on paper before you start coding blindly. So we're going to do that part. First part will be to take a type theory and make it ready for implementation. Okay, so first of all, also for people on Zoom, if there are any, the slides are now available on my GitHub. So I think if you just type info type theory, I'm currently hit number 2 on DuckDuckGo. I don't know if I'm first GitHub. So, okay, so let me give you an overview of what we're going to do. Okay, so in today's lecture, we're going to take a type theory that is presented in the, what you would say, the usual style. It's more or less the kind of rules that Frederick was showing in his lectures. And then we'll think about what it takes to implement them. And we're going to see that the way they're written directly, you cannot just put them into code. So we'll transform them to something that I would call algorithmic rules or algorithmically presented type theory, which in particular uses something called bidirectional checking, type checking. And we also have to think about algorithmic type checking, how to actually check algorithmically whether things are equal. Then in tomorrow's lecture, we're going to implement what we cook up today. We're going to implement it tomorrow in the simplest possible way. Okay, I'm not going to explain too much about what we're going to do tomorrow. And in lecture 3, we're going to add what's called holes into our proof assistant, the proof checker. Holes are things. They're like unfinished bits that you want somebody else to do. For instance, unification. And the holes are the basis for many techniques in proof assistance, such as type class, arguments, and others. So they're the first thing you want to put in, because once you have that, you can do lots of other things. And then the last lecture, we are going to experiment with using computational effects, in particular handlers and algebraic operations, to see what the space of design there is, so that you can see maybe an alternative way to implement some of the things that are usually implemented sort of in a straightforward functional style. We're going to try to use effects. Okay, so let's go to the first lecture. And by the way, if you have any questions, please ask. I think I only have one kind of commas, so I'm hoping there will be no questions. Yes, but even if you have a question about commas, feel free to ask. Okay, so let's start with sort of useless or maybe deep question. What is a type theory? You have a question?
Sorry, the first hit on DuckDuckGo, Faust's theory, is a board game, which is unrelated.
Second,
the first hit on DuckDuckGo for Faust's theory is a board game.
A board game. There's a board game called For Type Theory.
Yeah, and it's foxtheory.com.
Okay. I'll check it out. We'll check it during lunch. See if any good. Okay. Let me come back to what is type theory. So yes. So type theory. There are many views of what type theory is. It's a bit like what is space in mathematics. There are many views of what is space. It can be a metric space, a topological space. It can be, something quite like it can be sheaves. So all those answers are useful, and also all these various approaches to type theory have their own purposes. I believe, so we're going to hear a little bit or a lot about SOGATs from Andrej in these lectures in this school. And that kind of, the kind of thing that Andrej is going to explain is much more mathematical in nature. Whereas for implementation, we want to stay close to something very syntactic. So we are actually going to work not with what I would call a type theory as a mathematical object, but with a presentation of type theory. So in general, in math, when you say presentation, that means you have a way of displaying information about the thing. Like, for instance, what is a presentation of a group? Well, a presentation of a group tells you that you have a list of particular symbols called generators, and then you have a list of particular equations. And that's not a group, but it presents one, right? So in the same way, I would say if I give you a bunch of inference rules, that's a presentation, a syntactic presentation of a type theory. And that's what we're going to do. So let's begin. We're going to make our type theory as simple as possible so that our implementation isn't very complicated. But on the other hand, it should contain enough features to make the implementation interesting a little bit and a little bit challenging, a little bit complex. So we're going to have a type theory that has type, universe type, products, dependent products, and then application and functions, which go with the products, of course, and local definitions. So there will also be local definitions. Now you can see here that it says that certain variables are bound in certain terms. I'm not going to explain the details of this because Frederick was already talking about bound variables and free variables. And in any case, we are going to have to deal with this in the implementation anyway. And my advice would be, if you really want to understand bound and free variables, implement them and debug. And then you will understand them. And you will also just do this just once and never again, I hope. We're not going to implement them. We're going to, it's much, much better to use a library that does it for you. Okay, so these are going to be the components of our type theory. We're going to see the rules and all of that in a moment. I just wanted to show the syntax, what it's going to be. I am not putting any commas here randomly, and I am putting a dot here randomly. These are random traditions in type theory and logic where people like to use too few parentheses and a lot of punctuations. And once you've used them for 10 years, you can read them. But I've heard real mathematicians complain that there are way too few parentheses in type theory. So if something regarding the syntax is unclear, please let me know, and I'll put in some parentheses. The way you read, maybe just this, the way you read the local definition is like this. We define locally, so locally means only inside of the term u is x defined to be t. So let locally x be t in u. Okay, that's what it means. So it's a local definition. Now, why do I want these? The usual theoretical, like textbook definitions, presentations of type theory, they usually leave out local definitions. And that's because you don't really need them. You can get rid of them by just substituting, replace all the x's with a t here, and then it's gone. And that will, in fact, be one of our rules. But having these is essential for any kind of practical implementation. I mean, you really can't use the tool unless it offers you to define things. Because if it didn't, you would always have to write everything in full, and that's just not going to be doable. So we're going to have this to see how it's implemented. Okay, so the next thing to explain is what will be our judgment forms. That is to say, what kind of assertions we are going to make in our type theory. And there will be two kinds of assertions. One is that a term has a type, and the other one is the two terms are equal. Notice that this is type equality. Okay, so from a semantic point of view and mathematical point of view, you very much want your equality to be typed. It makes a lot more sense than untyped equality. So we're going to keep it typed here. And we will think carefully about at what point can we afford to forget the type, okay, when we're comparing it for equality. So what are these contexts? This was already in Frederick's lecture. There was some talk about the contexts, but the way you can imagine context is as maps, which give you information about variables. So we are going to have two kinds of information stored in a context. So you can ask a context, hey, what's the type of X? And if X is a valid variable that the context knows about, then it's going to say, it's going to give you a type. And the other one is X defined to be something. So our context can also store the fact not only that X has type A, but also that it's equal to some term T. That's also something that can be inside a context. Again, this is already the kind of thing you won't normally see in a textbook of type theory. There were textbooks of type theory, but let's say papers and PhDs. So some PhDs, of course, have this, right? Depending on what the PhD student was doing. Like there are lots of French PhDs that have this kind of thing in the context. Why? Well, because the French actually use their type theory, right? They don't just talk about it. So okay. Anything else to be said later here? Probably not. Let's, yes.
You could implement let with just lambda x u applied to t.
Yes, right? Very good. Thank you for asking the question. I will address it in 3 slides. Okay, okay. I hope it's 3, maybe 4. No, it's 1. I did not pay this person to ask. Okay, so here is a common fallacy I used to believe when I was a little boy. Okay, so isn't this local definition business that you define X to be U in T just the same thing as you have a function and maps X to T and then you apply it to U? And the answer is yes in a simply typed lambda calculus, no in a dependently typed calculus. Why? Because when we are type checking this T, we know that X equals U. But when we're type checking this function and type checking the body of T, we don't know that X equals U. It has to work for any X. And this makes a difference. Right? Yes. That's the difference. Yeah. Okay, so it's important. Now, if types are simple, then definitions of variables don't influence types because there are no variables in types because types are simple. So that's why it works for the simplified lambda calculus, but it doesn't work in general. Okay, so exercise. Find an example where the difference matters.
Is there a question?
Yes.
What about rank 1 polymorphism?
Rank 1 polymorphism. What about it?
Okay, I've seen it. Isabel actually defines let this way.
Yes.
But I've seen a difference. I mean, Isabel uses this Prenex polymorphy.
Yes.
Prenex polymorphism. Yes. And yeah, so that would be my question. So in the simple type lambda calculus, we know this is equivalent when we have Prenex rank 1 polymorphism, Hindley-Milner kind of type system. There is a difference because actually the type system has like a special treats especially these let constructs. So that would be my question. And
okay, so I think there are really 2 questions. Okay, so the first one is if you have Hindley-Milner style polymorphism like OCaml or ML or Haskell or Isabel at the meta level, then there will be variables in your types because you'll say for all alpha, blah, blah, blah. So first of all, that's a very limited kind of dependent types where your variables are actually type variables. And here we are assigning a term variable. So there's still no term variables appearing in polymorphic types, only type variables. And so this distinction is strong, and so it's not going to influence anything. So that's the first thing you asked. What was it? So Isabel defines one in terms of the other? Or what was it?
Actually, they have that construct in this defined precisely
Yeah,
this way.
so that's why you can still do it in Isabel, but there is also another point that's important from the programming language viewpoint here is in programming languages, if there are effects, then things are going to, it will be different, right? If you have some effects, like imagine it prints hello, okay? And under the normal reading of operational semantics, you're going to say here, oh, evaluate U, print hello, proceed to T. So you'll see one hello. But here, depending on what your strategy is, if you do it wrong, you'll put in you'll put in U many times or 0 times or whatever. So you have to be careful about effects when there are effects. But there won't be any effects in Isabel, so you're fine. So there's also that dimension that you need to worry about if it's a programming language. I don't know if I answered your question. But yeah, if you have rank 1 polymorphism, Hindler-Milne style, then you can replace one with the other if there are no effects.
Okay.
Actually, to be precise, do you need to give us the exact rules for both?
Which I will in about 3 slides. Yes. So far, I was just assuming that you've seen these things before. Yes. Okay, let's do the rules. Okay, so the way I'm going to write rules is as usual. I'm hoping everybody's seen a rule before. It's a fraction, and above the line you have premises, and below the line you have inclusion. And in gray, I'm naming every rule. I recommend naming rules and making little macros so that you click on rules and then you get them. Because without naming rules, there's a lot of confusion going on. But it's to you. So we have the variable rule that says that if gamma thinks that x has type A, then x has type A. Here you should read this is also if x is defined to be something, then we still think like if x is equal to t and has type A, it still has type A. Okay, I just didn't want to bother with another rule that says, hey, the other possibility if x equals t, it still has type A. So I hope you can read that way. Now here is the reason for the name of our type. Okay, we're going to have type in type. Yes.
Don't have Schirach's paradox from this.
Yes, this type theory is inconsistent, so more fun. Allows you to do more than just ordinary type. Why? First of all, this is a significant simplification in terms of implementation. If you have to implement something that doesn't have type, there is a significant complexity here. And I want to avoid this complexity because I want to keep my implementation very simple. In fact, you will see that most tutorials on how to implement type theory use type in type because this is such a strong simplification. It immediately gives you a lot of power. You can do all kinds of things. You can implement Girard's paradox. It's fun. But on a more serious note, I would also like to say that a type theory which has type in type is not itself entirely useless. It is only useless if you are trying to use it as a logical system in which to inhabit a type means to prove a logical statement. If that's how you're using your type theory, then of course it's stupid if you can inhabit every type, because then, everything's true. But it's not at all stupid if you think of a type theory as a computational system in which you want to compute. If you want to compute and you want a Turing-complete programming language, such as the one that we're going to have, then yes, every type will be inhabited. And that's just a feature of computation with general recursion, that you can use recursion to inhabit any type. Yes?
Is it too? I mean, for instance, Unimap in Rock, you use it type in type. And even not caring about universe, you can still catch, 95% of the errors you would make on paper?
Right. So the question is, there are libraries, like Unimath is one of them. It's a univalent mathematics implemented in Rock, which turns on type in Coq. So first of all, the fact that Coq allows you to turn on type in type should tell you that, it's fun. right? It allows you to do it. So I once asked Benedict Arends whether they ever accidentally made an error because they have type in type, and whether they worry about it. And so the answer is they worry about it. And Mike Schulman on persistent stack exchange gave an example where he actually hit this problem. He thought he had a theorem which disappeared after you turned off type in type. So, you know, it takes a Mike Schulman to accidentally use type in type. Otherwise, it's kind of insane. Also, I should say that Voevodsky was very much in favor of doing type in type, and he wanted to check consistency later, whatever that means. I never understood that. Yes.
Are there any ways in which you can consistently and usefully have type in type to do logic? In analogy to, for example, in new foundations, where they have a universal set, so they can have set and set that, and you can still, in fact, people have proved the consistency of new foundations. So, is there anything similar for type theory?
Okay, so new foundations has it's got a certification at the syntactic level, which is what saves it, right, from these straightforward set theoretic paradoxes. I mean, my answer is you need to stratify something. That seems to be the only solution we have. If you have this wild type that just allows you to do anything, then you will do anything. So, but what is a stratification? Well, it's type 0, type 1, type 2, type 3. You can have a hierarchy of types, of type universes.
Right.
So that is a standard solution. So, but maybe you want to stay here, but then still have some other mechanism that allows you to verify that you're consistent in a particular case.
So I would see that the universes solution as analogous to the set theory solution with Grothendieck universes, but then I see the new foundations solution as a kind of third option. So is there some third option here, or is this something that I just don't care about?
The solutions that I've seen always create a hierarchy of type universes. Maybe it's just type and kind, so then it's 2. Maybe it's an infinite chain. Maybe it's omega plus omega many for some bizarre reason. So just usually they default to that. I think the reason is that it's well understood and it kind of works in implementation. I suppose you could look for some more syntactic stratification a la new foundations in lambda calculus. And I wouldn't be surprised if somebody has thought about it. If anybody knows about this work, let us know. And if it doesn't exist, you should do it. But then you might have a problem defining, showing consistency.
Yeah, I have no desire to go anywhere.
Okay.
Like new foundations.
Okay, so let's keep going. So there is a rule for products, which says that in order for a product to be a type, its components have to be types. We've seen this one. Application and lambda. I don't think I need to stop much here, other than to note that it's just 1 comma in this rule. So hoping you're fine. I do think that. So here is the impolite thing the type theorists do. See this time? Okay. So if you're a type theorist, it's super clear to you that this is term : type. But if you're just like a random person on a metro and you show them this, and it's like, they won't be able to read this. So it would be really more polite to put parentheses here and possibly even here. But for some reason, that is not done in type theory. I don't think there would be anything wrong with doing it. Okay, so there's the rule for let, and this is the rule that actually puts definitions into context like this. Okay, so let's see. So if you want to type check let, first you check that P has a type A. Then when you type check U here, you put in the information that X equal to P and that it has type A. So far, we have not seen any rules that actually use the definition. They will appear in equality rules. There's a bunch of equality rules coming. These are just the terms and types. But this is how you store the information that X equals to U in the context while you are type checking. Sorry, that X equals T while you're type checking U. Any questions here?
So how do you introduce this in the context? This is the elimination or those kind of contexts.
Sorry,
How do you introduce this equality in the context?
I just say that contexts may contain this information.
Well, there should be an introduction rule for extending the context like this.
Well, I think you can read this as an introduction rule, right? What do you mean? So introduction rules. Okay, so let's see.
I'm wondering much whether you need any rules for well formation of context.
Are you asking how do I know that this context makes sense?
Yes.
Yes. That's something that I want to sweep under the rug a little bit. We could be very careful about explaining what it means for a context to be valid, and you need to do so because sooner or later you need to use the fact that your context doesn't contain any garbage. So you're quite right that we need to have such rules, and if we did have them, then we would be able to tell that if gamma is a valid context, this is also going to be a valid context because we carefully type checked T beforehand. See, this premise is going to make sure that I'm not putting any garbage into the context. If that's a question. But yeah, well, I would have to be more explicit about what is a good context. So a good context is a context that doesn't produce garbage. That's how you should think of it, and then you can try to write down rules that will ensure that. Any other questions? Yes?
Why do we replace X with T in B?
That's a good question. Here, let's think about this. So because there is X in this context, B is allowed to mention X. But down here, B is not allowed to mention X anymore. So we need to do something about it. What could we do about it? One possibility is that we replace X with T because we know that they're supposed to be equal. If you're in implementer, you're going to worry here because this could mean that B will become really large. Because if X gets copied around, you're going to make many copies of T, and that is a problem. But what is an alternative? Well, an alternative is to have a let statement here as well. I could say here, let X equals T in B, okay? But that's the kind of thing I don't want to go into right now. So I don't want let statements in types, although it's a perfectly reasonable idea, and you could have that, and it would make a lot of sense to do it. Just for simplicity, I'm not doing it here. But a very good question, because often you have to think about what happens in the implementation often is that something that seems mathematically like the natural simple thing to do can be quite costly in the implementation and also in a kind of hidden, unobserved way. So here we say, oh yeah, but we can just replace, right? We can just replace X with T. What's the problem? Well, the problem is that if there are two X's in here, you've duplicated T, and now you imagine that this happens a couple of times and you immediately have an exponential blow up. So you have to be careful about these things. Okay. Let's be a little bit more careful about how we write the rules. Let's think about something here. Okay, so if you look at these rules, in Lambda, I'm checking that A is a type. But in application, I'm not checking that A is a type anywhere. That seems a little bit random. Also, I'm not checking in either one of them that B is a type. So you should always worry about this. If there is a little piece of syntax that doesn't get checked anywhere, how do I know that it isn't garbage? Maybe it's garbage. So why isn't A garbage here? Where did it come from? Like, why is it okay? So if you were more careful, you would write these rules with more extra premises in blue, like this. You would say, oh, I want to be super careful. I'm going to check here that B is a type, and I'm going to check here that A and B are types. So these blue things, their purpose is to make sure that the rest makes sense, that the types appearing in the other parts and the context appearing in the other parts of the rule are okay. So they're sometimes called presuppositions. So the things that you need in order for the rule to even make sense. So without the blue one, here, right? You can say, well, for this to make any kind of sense, B should be a type. If B is just some garbage, then we have a problem. Right? So the presuppositions are important because they make sure that your rules are sensible. So in a way, you would want them. In another way, in another sense, you don't want them. For instance, if we think about implementation, okay, having this premise and having to check this premise by a type checker may mean that I'm going to check that A is type, that the A is a type twice. I would very likely check that A is a type here. Why? Because the pi, if we go back, the pi rule will already check that A is a type. So when I come down afterwards, now I'm rechecking that A is a type. Yes? So what? Well, I checked it twice. Now imagine this stacked up, you're going to end up doing a lot of extra work. So we want to avoid this. We want to avoid unnecessary premises, checking premises that need not be checked. And these are presuppositions. So, you will not avoid checking things you actually have to check. So rules can be given in two kinds of ways, which I call, some people have called economic, and well, the other one is, I suppose, non-economic. So the economic one would be where you try to remove these premises that would cause you to check things twice. But you have to be careful how you do it, because if you remove too many, you will let some garbage in. So you have to be careful about this. So what you want to do is, you want your type theory to satisfy certain theorems that tell you that the type theory, or better, the presentation, the rules that you have, that they make sense. So there is a presupposition theorem which would say something like this. This is a no garbage theorem. If I manage to prove that T has type A, then A should not be garbage. Then I can also prove that A is a type, or derive, I should say derive, okay? And similarly, if I can manage to prove, if I can derive an equality that T and U are equal at type A, I should be able to derive the fact that T and U actually have type A. And then if you use the first line, you will be able to derive that A is a type also. Right? So that's a theorem that will tell you whether you deleted too much stuff. When you have your rules and you think that some premises maybe are not necessary, well, try proving the theorem, then you know you're okay. Yes?
How hard is it actually prove?
This one is not too hard to prove. This is just a structural rule. So you have to set up
also the conversion rule that kind of
the conversion rule, which is coming.
I think without the conversion rules, it would be really easy.
I don't. No, I don't think the conversion makes any problems for you, because you just have your induction just goes through the conversion saying if you manage to prove that A and B are type, that A equals B, then they're types. So if I remember, Theo, where's Theo? Did you formalize this when you were a little boy? Right? It wasn't super complicated, right? It was just an annoying structural recursion.
Because I know that for some variants of type systems, it's hard to even show subject reduction because of.
Oh, but this is a lot easier than subject.
Yeah. But I think there is some problem which look like this, but
yeah. So let's look at some other theorems. Sorry.
No.
Okay. Yeah. So let's look at some other meta theorems that are desirable for a type theory to have. So one of them, which may or may not hold, but it's a lot easier if it does. It's a lot easier to work with your type theory if it does. Is uniqueness of typing, which says that if you can show that T has type A and that T has type B, then you can also show that A and B are equal. That's uniqueness of typing. And then there are two more basic ones, weakening and strengthening. But I warn you that these are not exact statements because I'm using notation that I did not explain. I just want to give you a sense of what it is. The last slide contains references where you can read the exact statements for these. So one of them says that if you have a context, and in this context you can show that T has type A. If you put more stuff into the context and you get a larger context, you will still be able to show that T has type A. So introducing more variables does not invalidate, or more definitions does not invalidate all proofs. This is important for implementation, because what is going to happen is the user is going to derive something over here, And then inside some lambda abstraction, they want to use it. Why can't they use it? The lambda abstraction has extra variables, weakening. So this is important. Strengthening goes in the opposite direction and is more treacherous. Okay, it says if I do something in a large context and I want to reduce the context, I want to make the context smaller, can I? Well, certainly not if T mentions variables outside gamma. But suppose that T only mentions variables that appear in gamma. Can I then cut down and just throw away all the variables that are not mentioned? And I should possibly say here also A. I forgot that I also need to check that the three variables of A appear in T. So there's a mistake on this slide. Also do it for A. So this is called strengthening. Not all type theories have this property. But as soon as you lose this property, it becomes an order of magnitude harder to implement. So, because it's super easy to make a mistake and assume that you have strengthening. It's hard to avoid strengthening in the implementation. It happens, like for instance, a typical what would happen is, okay, look ahead for people who know about this. During unification, you find out that some variable equals nat, okay, which is a constant. And you say, it's a constant, I can set it to nat. But you're inside the lambda, how do you know? Because you're now trying to take your constant outside of a wider context. So this, you have to be careful about this meta theorem. And our type 3 is going to satisfy it. So a famous rule that breaks this property is equality reflection, if you look at it. Okay, let's go on with equality. So there are the equality rules come in batches, and I'm going to show you equality rules that are slightly different, or actually quite a bit different from Frederick's. So how do they go? The first batch just says that equality is an equivalence relation because it is reflexive, symmetric, and transitive. So we're not going to belabor this point. This is a super important rule. It's called conversion. This is the reason for having equality. It says that I can replace a type with an equal one. Okay, so if A equals B, if T has type A and A equals B, then T has type B. So a typical mathematician's reaction is going to be obviously, but this is the 50% of the implementation is about this, okay, or more. It's you have to think carefully about what to do here. Why is this rule tricky? Because I can use it it looks like I could use it at any moment. At any moment when I'm trying to prove that T has type B, I could ask myself, but what if there is a type A equal to B, such that T has type A? It would be easier to do this than to do that. This rule can be applied at any moment. We don't like such rules for implementation. When we're implementing a type theory, we don't want rules that could be applied at any moment, because then we're going to implement Prolog or worse, right? Which will just blindly search for things, and it's just never going to do anything. Okay, trust me, it's not going to be efficient. We want to cut down on opportunities for using rules, and this one is particularly bad. All of these are particularly bad. Whenever you're trying to prove an equality of any kind, oops, this should be a U. If P equals U, this one should be a U. If somebody can zulip me typos, I'd be very happy. Or write them on a piece of paper. So I had 2 so far. Or just tell me how many bugs have a count. Just have a count and then tell me how many have okay. Like find 5 errors. This one also, this one should be a U. Yeah, it was very nice. So I'm up to 3 now. I can do this myself. Okay. Yes. Or if you ever want to really understand type theory, implement it. You have no chance of doing it right just in slide or paper. So there's a gamma missing here. Okay, so we want to cut down on these possibilities eventually. But let's look at the rules. Okay. So then we have the rules. Somebody asked you have to actually tell us the rules for equality. So here's one. If you know that X is defined to be T, then your type theory actually knows that x equals t. That's how you use the fact that the context is telling you that x is defined to be t. Okay, now come the rules for functions. And there are two rules, and these are, one of them is an extensionality rule, and the other one is a computation rule. If you look at the literature on type theory, you will see that this is a general division, but here I'm presenting extensionality rules instead of eta rules. It's more common to speak of eta rules. Exercise, it's one of the exercises on my slides in the speaker notes, is that show that in the presence of all the other rules, this extensionality rule can be derivable from and derives the rule of functions. So if you don't know what I just said, then you will have to look up the rule for functions. But the best way to do that is to find somebody who already knows and then do it with them. So here's the rule. It says, suppose we're trying to compare t and u, and we see that they are of a product type, so they're functions. Then to compare them, you just apply them to a variable, a fresh variable, and you repeat with the comparison. And oh, there shouldn't be a b here. Okay. So like this. So compare them at a function, apply them. Now, what's the benefit of this? Let's observe. So the terms got bigger. T became T of x, and U became U of x. Okay, but the type got smaller. Instead of a product, it's just the body of the product. So that's something. Okay. And the other rule is the usual rule for beta indices. So it says that if you have a function applied to an argument, you just substitute. What is the probability that I got this one correct? Okay, so let's be careful here. Let's see what we checked. We checked that A is a type. Why did we check that A is a type? The stuff that is down here, okay, you need to make sure that you don't let any garbage in. So this is something that the user may have written, so we better check it. Think of it that way. And then, especially whenever you put anything into the context, you have to ask, how do I know this is not garbage? Ah, because of this. Okay. Now, this should be the case everywhere. Whenever you see that something goes into a context, you should know that it's not garbage. So then this is a little bit suspicious here. Okay. Maybe we should be checking that A is a type. Who knows? Okay. It's not clear. Is it a presupposition which I can take away? Can I throw it away, or do I not throw it away, or how is this going to be implemented? Anyhow, this is just saying that this is the usual beta rule. We need to now take this stuff and turn it into an algorithm. And the way it's written, it's not really an algorithm. As I already said, it doesn't give you any straightforward way of applying the rules, because some of these rules could be used at any moment. And then you need some way of knowing when to use the rules. So these kinds of rules, and these are the kind of rules that you usually see, are often called declarative style, because they just declare what the rules of the game are, but they don't tell you how to use them to get any results. So declarative style. By the way, I think Frederick had this written with the, which one? No, not yet, later, when I have bidirectional, I have the algorithmic one. Any questions at this point? Yes?
You managed to prove the meta theorem. A equals E in type premise become blue, sort of redundant.
Where? In which rule?
You said the meta theory said if T has type A and T has type B, then A and B are equal.
You can prove. There is a proof that A and B are equal. Yes.
Okay, yeah. So I can't remove it from the rule here.
No, because it might be very difficult. It might be quite difficult to actually derive this fact.
Okay, yeah.
This doesn't mean they're syntactically equal. They could look very different, but then when you do all the reductions and you use this rule and use that rule, and you manipulate them, you see that they're equal.
Right, but it's not like I have the meta theorem. It's a function I apply it to those two proofs, prove that T has type A and then prove that T has
Oh.
B, and then the premise A seems to be falls out.
Yes, so what you're asking is, if I understand you correctly, if we had a constructive version of this theorem,
Yes.
because it's constructive, it would give us an algorithm that
Derive the proof of A equal B.
yes, but you would then have to prove that you would have to prove something about T twice. You're not getting any
Right.
free lunch. You have to prove that T has type A, and that you have to prove that T has type B, and then your algorithm will tell you that this is the case.
But the difference is that this rule actually gives me the proof that T has type B automatically. Or agree.
You mean that?
Yes.
Well, it's not free. I mean, you still have to do this.
Right. Okay. Yeah.
Yeah. Okay. So whichever way you're shuffling it around, you need to provide two to get the third one.
Yes. Okay. Right.
Yes. Great. Thank you. Okay.
Die Schule together.
What is the question? What is the question?
Where the rule has no gum.
Oh, yes. Oh, yeah. I think, no, I counted that one. Thank you. No, I really don't. If I overcount, I'll have a sleepless night. Actually, maybe I should overcount on the assumption that some of you are gonna maybe there will be an error that everybody misses. If there was a question?
Yeah, I just didn't understand if the three rules of before, like the structural rules on the slide before again, and were actual theorems, or we just want to assume them?
Oh, this. These things. All of these things are what I would call meta theorems because they are theorems about the rules. Yes, and you would have to prove them. I'm just showing them to you so that you see them and then you start to believe that they're important. It's a totally different matter how you prove them. It can be quite hard. Sometimes, for instance, you have to use math to not just, oh, I'm typing this in ACTA and then I'm pressing Control C all the time. Yes?
Don't you have a kind of meta theorem that if T has type A, then the free variables of A appear in T as well?
Ah,
That's why
you're trying to say it by strengthening here.
Yes.
Yes. So one way to say strengthening is to do exactly what Andrej is suggesting, that if T mentions a variable, then A also has to mention that same variable. Is that what you're saying?
The other way.
No, the other way. Sorry, if A mentions a variable, it has to appear in T. For nice theories, that's going to be the case, yes. Good point, thank you. Okay, so how do we turn this into an algorithm? Well, here's the basic idea. If you stare at these rules here, you see that some of them are kind of easy to use, and they already tell you what's going to happen. If you see type, you want to say, well, its type is type. If I see a variable, I know precisely how to get its type. I just look it up in the context, right? Which one? No, this one also. Okay, so it says, I see this. How will I get this? Well, you will go and you check that A is a type and compute the type. So it's kind of, some of the rules by themselves want to give you the type of the term. And so the idea is that we're going to use this fact and we're going to rephrase our type theory in something that's called bidirectional type checking, where we replace the typing judgment with two different typing judgments. One of them is the inferring, and the way to think about this one is, you say, in context gamma, we can infer that T has type A. So think of T as input and A as output. You give T to your algorithm and you will get A out. So some rules are good for this kind of thing. But then we also need something else. We are sometimes given both T and A. So they are both input T and A. And then we want to check that it is the case that T has type A. So that's the other task that we have. So here A is output, T is input, A is output. Here both are input. And we want to check that this is the case. That's how we want to write our rules. Okay? But not in any arbitrary way. So we want to do this in a particular way because we are looking for an algorithm. So the rules should be deterministic. What does that mean? That means that in any situation at hand, you can, at most one rule applies. You don't know, you never want to be in a situation where you have several rules that you could apply, because then you will have to try all of them. And if one of them doesn't work, you'll have to try another one, and you will do backtracking, exponential, blah, blah, blah. Not good. We want them to be deterministic. Not only do we want to be deterministic, we want to be easy to tell which rule to use. If it's hard to tell which rule to use, that's not very useful. If we have to, this is something complicated. So one way to make sure that it's easy to tell which rule to use is to say the candidate rule has to be obvious, apparent, from the syntax. Or sometimes it's the syntax of A, so syntax of T or A, okay? But you look at T and you look at A, and it should be like, oh, T is a lambda, I know which rule to use. Oh, T is an application, I know which rule to use. So that's how you should structure your rules. Like, you want them to be syntax driven. Okay? Also, yes.
Are those two the same point phrased differently?
The second point as a refinement of the first one. You see, in principle, it could be the case that only one rule applies, but you have to calculate the fundamental group of some manifold to find out which rule.
Yeah.
You know, there are mathematicians in this room who would be able to give you a type theory that's like that. So you don't want that. Right? It's a refinement. This one it says not only does only one rule apply, it's easy to tell which one. Okay, so we also want to have a relationship between this type theory and the original type theory. And again, these are meta theorems that I'm not going to prove, but if you want to be serious about your implementation, you should have a PhD student who proved this thing for you. So here we go. So soundness is going to say, if I can do something in my new type theory, then I can also do it in the old type theory. And completeness says, if I can do something in the old type theory, I can also do it in the new one. Okay. And since in the old type theory everything is input, I give you T and then you have to check this, it's going to be checking mode. Yes. Now, without these theorems, it's very, very easy to do this. So if I delete completeness, okay, then I can do this. No rules, empty theory. Empty theory is fine, right? It's sound. It doesn't prove anything, so it's sound, but it's not complete. Okay. If I delete soundness, it's very easy. I just write the rules to derive everything. So you need both because they balance each other. Any questions? So let's see. So now we write the rules. So how do you get the bidirectional rules out of the original ones? What you do is you look at the original rules and you ask for each one of them, do I want the wiggly arrow to go this way or do I want it to go that way? Okay. And if you think a little bit algorithmically, usually you can figure it out. Okay. So that's just like a very naive recipe. There are serious treatments of this bidirectional style with research papers and all that that you can read. There's deeper math in there, but we're not going to go into this. Okay, so variables already know, so think of it this way. If the term knows what type it is, then it should be inferring. So yeah, find out what the type of X is. You just look it up in the context and then you output it. Okay, we know what the type is. We just say it's type. Okay. Now here we have to be a little bit careful. We know what the type of pi is. It's type. But we must be careful not to let any garbage in. So we cannot just say type without checking things. We also have to check that A is a type, and now this is checking. I want to say check that A is a type, check that B is a type. So the checking stuff is appearing as premises to inferring. There's going to be an interplay. They will call each other. Right? And the type checker will go from one mode to the other, and it's going to exchange. That's how this will make the information flow go through. Okay, so let's see this one. So how do we, if you have an application, do you want to check its type or do you want to infer it? And so let's go back to the rule. Take a moment to see how to figure out that this needs to be inferring. Okay. Here. Okay. if this is to be checking, checking means somebody's going to give me a type C here. And I need to check that it has type C. My first step will be to magically undo this C and write it as B with U of X. Okay? So if I just give you a type and you have to do this rule, would have to now magically convert C to something of this form. That's already doesn't look right. Okay. You don't want that. So let's try inferring instead. Okay, so if I infer the type of T and it's a product, can I do the rest? Yes. Once I figure out that T is a product function with this product type, I can do the rest. I can take this A, check that U has type A, check. Not infer A again. I already got my A from here, so I'll check it here. Yeah? You will never infer the same thing twice. That's you infer it once, and then in the other place you stick it in for checking. And then B, yeah, I can output B because I have it. I have everything. Okay? So that's why it's going to be inferred. And lambda similarly, if you think about it, so inferring. Okay, so these are the inferring ones. Okay, let binding is interesting because it's direction agnostic. Let binding is not so much about the terms that we're deriving, the checking. It's about the environment in which this is happening. Let binding, so local definitions, they influence gamma. They don't influence anything directly, immediately that's going on with the term and the type. So you could, if you see a let in infer mode, you just go in and do it. If you see a check, you go in. So it propagates inwards. So somebody wants me to infer this. Okay, what do I do? Oh, okay. First of all, I need to figure out what this A is. How will I, where does the information come from where this A is? Well, it has to be the type of T. So I'm going to infer the type of T to be A. So I infer this one. Stick things into the context. And because they want me to infer, I will infer the type of U, and it's going to be some B that can mention X. And then, oh, wrong notation for substitution. It should be B with T replaced by X. And then checking is very similar, except now the type goes in. And there's a subtle point here that you will see that B here cannot mention X. This B is valid in gamma. We will make sure that it's valid in gamma, so it's not mentioning X, but it doesn't matter. It doesn't matter. It just goes in. Whereas this B that comes out can mention X, which is why we have to replace T for X here. Yes.
But we know that X is equal to T.
In B. Yes.
We still need to substitute T.
Yes, because X has disappeared. Sorry, there is no X anymore. That's why. It's similar to the question we had before. Why did they do it? Because X disappeared. I could again say here that the result is let X equals T in B. But for simplicity, I'm just not, I don't want to see these lets in types. But also, I suspect the user doesn't want to see lots of lets in types. So let's not do that.
How do you get the check, the let, check let thing?
Where did this A come from?
The other A.
This A?
Yes.
This is inferring mode. So inferring mode will be implemented as a function that you give it T and it outputs A.
Right.
So read this one as this is input, this is output. Whereas if it goes this way, both are input. Okay? Yes?
How do you know which one of the two to apply?
Because I am either somebody is going to the task will be please check this or please infer this. The task is not going to be I have a T and A. Okay, you have a T and A. Do you want to check or do you want to right? So if somebody has just a T, then you can say, oh yeah, you have just a T, we know you want to infer. But if somebody has T and A, then they want to check. So just as to what's in your hands, you know whether you need to infer or check.
You ever want to infer gamma?
Gamma? Gamma is going to be quite special. It's going to be sort of like a general environment in which things are getting computed.
But in some contexts, you say, I have a theory, it's linear. Okay, now I have X and I have the type of X. If you infer the context, I can only
What do you mean infer the context? Oh, like get the smallest context for which this would work?
Or what? If it's a linear theory, then there is only one.
Okay, so first of all, this is not a linear theory.
Right, but otherwise, yeah,
Ah.
smallest context that satisfies.
Possibly, that would be an interesting thing to explore. Yeah.
Could you repeat why we don't have to substitute in the checklet?
In the checklet, we don't have to substitute because this is going to be input that is valid in gamma anyway. So it doesn't mention X.
Right, thank you.
Yes. But here we will get B as output, and it may mention X, so we didn't use that. Yes.
So there could also be a check rule for lambda.
There could be a check rule for lambda, where I wouldn't, if I didn't tell you the type of A here, if it just said lambda xt, then, so imagine a lambda without this A, okay? Now it's not inferring anymore. You can't tell what's going on. If you just see, so imagine you just see lambda x dot x. Okay, it's some sort of an identity, but you don't know at what type. So if it is without this type, then you need to do it differently, and you need to do it in the checking mode, and the implementation does it. We will see in the implementation that it also allows a lambda without the type, in which case it's checking. Okay, there's one more rule which allows you to switch from checking to inference. Why do we need it? Maybe somebody wants us to check the type of a variable, but the variable wants to be inferred. There is no rule for checking a variable. There's only a rule for inferring a variable. So what we do is we also have something that allows us to switch. Somebody wants us to check that T has type P, but P is an inferring term. That is to say, it's of the kind where you see, oh, I want to use an inferring rule here. In that case, you are going to say, okay, I infer the type of T, and I'm going to get some A, and then I will check that the types are equal, and then it's okay. And now we reined in conversion. Conversion is now not applicable everywhere. It's only applicable in this switch from checking to inferring mode. It's the only place where we need to check equality. So if you look back now, the rules are written in such a way that they are syntax driven and they are deterministic, and we know how to put them into code, and we will do so tomorrow. We just have to deal with how do you check equality, because we also need to have an algorithm for checking equality. Yes.
But if you have infer check, why do you still need check that?
Again,
Is it non-deterministic?
yes, you're right.
Because
Okay, I'm going to chalk this one up as an error, a bold-faced error. It's a conceptual error.
it's not deterministic.
So the point is this: I can just remove this. Okay, it will be better. Now it's really deterministic. Even more, right? Now I also have an answer to the question earlier: how do you know which one to do? Because okay, thank you. So you see, yeah, so I'm safe. Okay, delete this one, and then if you want to check a let, this rule kicks in. Otherwise, you infer a let.
Question.
Yes.
Can you program in a way that you never have to evoke infer check, or it never gets evoked? What? Like if you only write normal, something like this.
No, I don't think so, because even if you have just one variable applied to another variable, the variable that's in the argument will want to be checked, but it's inferring. So I think it's difficult to do this. I also will come back to this now and correct myself. See, I can think in parallel while I'm answering questions. So there is a benefit to this. This one propagates the information inwards. This one makes B go into U. But if we remove this and say, whenever you're checking a let, infer it first, then you lose any useful information that B might have. about what you need to do. So the rule that, let me, so I'll just write down the example and it should be clear. Suppose you want to check that that equals something, I don't care what it is because I'm not using it. Lambda y. This example where you have a y, where you have a lambda that's checking. I could probably come up with a similar example. This one is the easiest one. This is the only thing I could think about because I was also have to answer to Ambrose at the same time. So it's difficult. So take this one. So now
the type in the lambda abstraction, right?
say again.
You're removing the
Yeah,
type.
if I remove this, so I want to show you how it is useful for type propagate in because it informs the type checker. So using this rule, now we will end up checking that lambda y has type A arrow A, and that's quite useful. But if I try to replace this without this rule and say, oh, just switch to inferring, I'll switch to inferring and I'll try to infer lambda y and I'll say, I don't know how to do it. Even though the information is waiting for me out there, if only I could bring it. So there is some
the type notation, I guess.
and these kinds of things happen in many other constructs. So it's useful for it is in general useful for the type checker to not lose information if it can make it, if you can push it in. And this is not the only place where this kind of thing happens. Yes.
But your meta theorems, they were about the clarity,
Yes.
style, judgment by Scholar, but now with this style, you get the several versions of meta theorem.
Okay, so I'm not seriously suggesting that we use this kind of lambda right now. Okay, this is meant to illustrate that if you have such lambdas, then you will want this kind of checklet because it is useful, right? If I allow lambdas without type annotations, I have to rethink my theorems. Yes. Yes.
So for Ambrose, if you write everything in normal form, then this infer check rule happens when you switch from normal to neutral.
There you go. Okay. We have 20 minutes to do algorithmic equality checking. Plenty. Actually, algorithmic equality. Oh, are there more questions at this point?
Yeah, I don't understand. So this is no more deterministic.
It's deterministic once you see the bottom line. Deterministic means if you're trying to derive a given judgment, yes, there is at most one derivation. So if I tell you that we're checking, then it's deterministic. If I don't tell you anything, I mean, but it's a bit like this. If I just give you a term, the only thing you could possibly do is infer. If I give you a term and a type, well, presumably you're going to check. So in a way, it's still deterministic, except in this case, no, even in this case, it's not a problem. So, by the way, this deterministic business, this is not philosophy. This is just a desire to have a type theory that I know how to code up, Camel. Okay, that's a lot better than philosophy because we're going to get something working out of it if we do it right. You can also do it slightly wrong, and it'll still kind of work. Questions?
More remark that even in the case where we have two rules to check left, we still want to use the specific one because it lets us keep more information.
Yeah, exactly. Like this was the example where you keep more information by using it. Yes.
In the definition of completeness, will we gain something if we ask or also have completeness with refers to inference instead of just check?
What would it state?
Same thing, but move the arrow to the other.
That could be a little bit hard because some type is every term inferring? are there terms? If there are terms that don't have an inferring rule, you will not know where to begin. Right?
Can you infer any type that you can check?
That's a good question, and it's going to depend on details, right? If I have these kinds of lambdas, the answer is immediately no. So for our type theory, think about it and tell me later. I think our type theory is sufficiently annotated for everything to be inferring, because so here's a golden rule. If you look at your type theory, and whenever it introduces a bound variable somewhere, if it at the same time annotates that bound variable with a type, chances are you're inferring everywhere. Okay? Because the main source of not being able to infer is that you face a variable and you don't know what its type is. That's the main source that prevents you from inferring things. So if your type theory is such that diligently all the variables, all bound variables are annotated with their types, then that's a good indication that you will be able to infer everything, and then you could write maybe another line here. But I warn you not to take meta theorems easily, because sometimes it's hard to prove them and they're finicky, but you should still think about them.
Will we gain something? Could we just add a rule that says if you can check, you can infer? That makes sense.
Yes, so long as that doesn't ruin your flow of information, because I want to use this A as output. So I have to think about that. But yes, I think you, oh yes, actually you now suggested something that's in the implementation. It's called type ascription. We'll see it tomorrow. And tomorrow when we work on type, when I show you type ascription, you can tell me whether that's what you have in mind. There are lots of questions, yes? So
the answer good. In the sigma type constructor, there's no bound variable, but you can't infer.
The sigma type definitely has a bound
sigma type constructor.
Oh, you mean the pair? Yeah. The pair. How about the pair fully annotated?
Yeah. Okay.
So if you just write the pair, then that's more like this kind of lambda. So, which is a good point, right? Yeah. Which is one of the exercises, is write down the rules for sigma types, because you hit these questions, like the one that you just exposed, is that if your ordered pairs are not fully annotated with types, then it's not, then things are not as nice as they would be when they are fully annotated. Yes?
In the rules with the column, we had some rules about the quality, for example, transitivity. And I didn't see a direct parallel in the rules with the.
Very good. Yes. So what often happens is that you cut down on your rules. We threw away transitivity, we threw away symmetry, and so on. And then what we are hoping is that they are still admissible somehow. That somehow they're hidden somewhere in here indirectly. Yes. And that's actually one of the important points of, well, there will be, okay, sorry, here. There are now meta theorems that we should write. There is soundness and completeness for equality as well. And it's the speaker notes say exercise, write down the soundness and completeness. So your question can be addressed by completeness. If this is really complete, then if I derive something using transitivity in the original system, I should be able to derive it here without transitivity, because there is no transitivity here. So somehow transitivity is one way or another present, indirect. And this is a common feature that some of the rules, for instance, the weakening, which we had earlier, which said that you can make a context larger. Sometimes that's an explicit rule in a formal system that says you can use weakening. But in our system, it's admissible. So that is to say, if you have a derivation that uses it, you can get another derivation that avoids it. So it's a bit like that. Okay. So how is algorithmic checking going to work? It's going to have two phases. So to algorithmically check that P and U are equal at type A, there's going to be first a type-directed phase, where we look at this type A, and Depending on the form of A, if we see that it's a product, then we use the extensionality rule for products. If we had other types with other extensionality rules, we would use them in this phase. Extensionality rules would get used here. These are the rules that do not have a direction, and you can tell that you will use them by looking at the type. The left-hand side and the right-hand side of such rules is completely general. It's the type that tells you that you have to do it. And then once you run out of these extensionality rules, you switch to normalization phase. And many implementations of proof assistance avoid this phase altogether, by the way. They just have the normalization phase. So in Frederick's talks, there was just normalization. So there you normalize T and U. What does that mean? You bring them into some form that allows you to compare them structurally to see if they're actually equal in some way. So if you want to avoid the type-directed phase, then you would replace extensionality rules with eta rules. But then you have to think about how do I bring in eta rules into the normalization phase, and that is sometimes a tricky question for complicated concepts such as the unit plan.
Yes. So here for the applying extensionality rules, and also previously in like checking, we need to like have normal form types.
Right. So yes, this will be visible when I show you the rules. Okay. So we need to organize ourselves. So there will be, if you look at what words I'm using here, okay, we will definitely want to normalize things, which is compute normal forms. So there we are going to introduce this notation. T normalizes to U. You should always keep in mind that the word normalizes is a little underspecified. Do I mean strong normal form, weak head normal form, head normal form? There are lots of notions of normalize. We're going to use weak head normal forms. Okay. Because the only thing I require of normalization is that I need to see the top level of the syntax to make progress. Then there will be terms T of U at type A are equal. I'm just using a different symbol to distinguish my algorithmic type checking rules from the usual ones. So I'm just switching the symbol. And then there will be normal form comparison. And notice that this one doesn't have a type. Okay? This one is without a type. It doesn't need a type. Yes?
So when you split the phases to type directed and normalization, don't you first need to normalize A to be able to?
Yes, that was already a question, and it's here. Okay, it's on slide. It's on the next slide. Oh, well, actually, we'll come to it once we do normalization. Yes, I will address the point. Okay, so how do we normalize? So first, there are things which are already in normal form. So in terms of operational semantics, this is big step, lazy semantics. So type evaluates to type, product evaluates to product. We're not trying to evaluate A and B. We just leave them alone, unevaluated. Okay. So similarly, lambda is already it's already normal, so we just leave it alone. And then for the variables, there are two possibilities. If a variable doesn't have a definition, now we're in a territory where it's becoming a little bit difficult to write everything down with inference rules, so they are starting to look a little bit unnatural. It would be better to just look at code, in my mind. So a variable that doesn't have a definition just evaluates to itself. From a programming language point of view, this should be pointed out here that we are evaluating terms that are allowed to contain free variables, which of course you would never ever do in a program. A program is a closed expression. Right? Otherwise, when you hit a variable, you say, well, what is this? This is an undefined variable, right? You could try it in Python. It's lots of fun. Okay, so if it does have a definition, so now here are the things where something actually happens. If a variable does have a definition, then we normalize that definition, and then we use that. Here you should think, wait, if my variable appears 7 times, then I will normalize T 7 times. Yes, this is not efficient. And there is such a thing as premature optimism. First, have one conceptual, clear implementation and understanding of it, and then start optimizing. This would be a very nice point where you would want to optimize. but it's not easy to optimize this, because your first thought might be, if I have a t stored like this, maybe I want to replace t with its normal form. Bad idea. The normal form might be quite big, but maybe problematic. Or you would say, I'll store both. As soon as you start storing things, you should think about memory consumption. So it's never obvious, in my experience. Okay, how do we normalize a let? Oh, this is wrong. This is wrong. Right? Big, big, big. Okay, can somebody tell me what's wrong with this? It's silly that I substituted in. What I should be doing is I should extend the context with the definition and proceed, not substitute here. This should say x equals t, la, 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 la. Okay? Yeah. But there is also a little problem with types here. Okay? If I try to do this, because then I have to explain what the type of x is. So there's something interesting about implementation for tomorrow to think about this. Okay? The way it's written is okay, but it seems a bit silly that I'm substituting. So let's leave this one for tomorrow, because I think I'm running out of time. Okay, so how do we normalize? An application? There are two cases. You normalize t. If you get a function, you substitute in, and you normalize. This is just beta reduction. But if t doesn't normalize the function, which is a funny way of writing t did not normalize the function here. T is not of this form. See, this is a pattern. This is a pattern. So patterns are starting to appear. If a thing appears, you should carefully consider the fact that maybe it's a conceptual thing. And patterns should think, because I seem to be using it. And that would be important. So if it doesn't, it's going to normalize with something, and then you just attach new unnormalized to it. You don't normalize it. Okay. Okay. So, what kind of terms are we going to get this way? For instance, you will never get a let as a result of this. You can never have. You think of this thing as an input. This is input. This is output. What kind of outputs are we going to get? We'll never get a let as an output, because it just never features. We can get a lambda as an output. We can get a pi. We can get a phi. We can get a variable. Anything else that we can get as an output? We can get these kinds of applications, but they're special because this t prime, we know that it's not going to have a lambda in there. So these are kind of special. So this t prime is going to be something that is, again, a normal form, because it's an output. It's an output here. So it's an output. So, okay, so it could be something like a variable or more of these. So something's coming up. And if you look at these things, you will discover important concepts in lambda calculus. In particular, you will say, let's call this thing something. Okay? So here's what you can get. You can get a variable, you can get a type, you can get a product, you can get a lambda, which we just saw, or get something that has normal form applied to a term. But frankly, you can't really get all of these, because you're never going to get, this will never be a type. You wouldn't have a type applied to something, right? And also, this would never be a lambda applied to something. So this is not quite exact. So be more precise about what a spine is. Okay, so actually what we would get here is this one has to have a variable in the front, because you're never going to have a type applied to something so long as you are normalizing well-typed terms, or a pi, or a lambda. So it has to start with a variable, and that's important that it starts with a variable. So this slide is wrong. Here it should say a variable applied to a bunch of things, and that's called a spine. Okay, so I will fix this. So it should say x applied to some number of terms. That's an output. That's possible. That one down there is wrong. What I missed was the fact that I could bring in lambda. Okay, so we also have some lemmas here that we probably want. And so I use the programming language parlance for them. How am I doing the time? 4 minutes. Okay. So if T normalized, so here's the preservation lemma. It's preservation of types. So these are the sort of theorems you want to prove about this relation. If T has type A and you normalize it and you get a U, you better also have type A. Okay, terms should not become untyped or just get different types. This is easy to prove. You just go and you look at all the rules and make sure that you see. Okay, and the progress lemma would be that if you have a T, then it does actually have a normal form, right? That you're not going to get stuck or run forever. Right? You could keep applying the rules and you never come back. That would be one option. And we saw in Frederick's lecture, he showed this lambda x business. Well, that one would cause trouble, but it doesn't have a type, which is why here we're saying if T has a type, then it has a normal form. Okay, so finally the rules for equality. So here are the extensionality. This is the extensionality phase, and here is some. I think two people pointed this out. How do we apply extensionality rules? So I see that I need to check that T equals U at a type A. Well, the only rule that I could possibly be using is the product rule. So what do? I normalize A, and if it normalizes to a product, then I know A equals the product, so I can use extensionality, and so I proceed by comparing T of X applied to U of X and the fresh variable X of X. Okay. If it normalizes to something other, see here I have the first line is still this funny way of saying A normalizes to something that's not a product. Well, if it's not a product, then I don't know what to do. So I go to the normalization phase. And the normalization phase says normalize T, you get a T prime. Normalize U, you get a U prime. Compare them as normal forms, and that's it. Okay, how do we compare normal forms? Okay, here type equals type. A product equals a product if the components are the same. So A has to be C, but notice that the A is not normal anymore. Okay, in a normal form, the whole thing is in a normal form. That doesn't mean that all the parts are also normal. So A is not normal anymore. So I need to switch to back to typed equality here. So I switch compare A and C as types. So this is going to go back. Start doing this again. Same here. How about a spine? Oh, I don't have a rule for lambda, which is weird. Yeah.
We get eta expansion here because of the pi rule.
Second.
Do we get eta here?
We don't have eta. We have extensionality, but the effect is the same. Yes. If you type check lambda x t applied to x. This algorithm will tell you, okay, let me just finish this and I'll tell you how it works. Okay, so how do we compare spines? The way we compare a spine, so now these are like this, okay? So first of all, they both have to have the same variable. Then we get the type of x out. Then we normalize it. We get a product, it has to be a product, which has at least as many pi's as there are the terms, and then we go and we compare the terms Ti to Ui at a suitable type. So here again, we're switching back to typed equality so that the extensional rules will kick in. Okay. Why isn't there a rule for lambda? Because if we compared lambdas, it had to be at a product type. So instead, if it were lambdas, so here's your answer. If it were lambdas, then it would be a product type. So it would actually be, where is the extensionality rule? This case, so we would apply lambda to x and lambda to x. And then when we computed the normal form, the lambda would go away and we would be left just with the bodies of the rules. I hope I'm making myself clear here because I'm just waving my hands. But think about what this algorithm does. If you ask it to compare two lambdas, or a lambda in something else, add a pi type, and you'll see the lambda goes away, and that's why eta rule works. It has the same effect. Okay, I'm afraid I'm going to yes.
In the span rule, do you really substitute?
I think in the implementation I do, yes. I mean, you can always ask. You can always try to be a little lazy about substitution and do it sort of on the fly, or use explicit substitution. There are lots of techniques for avoiding substitutions, and I'm not trying to use all of those techniques. Yes.
If you look at the file for the slides on the last page, there's under like the reader notes or whatever, there's like 15 links and there's no visible text.
Okay,
It could be the way that your PDF viewer is visualizing the links. No, sometimes they're out of place with where the text actually is.
Everything else works fine. So
okay, I'll have a look. Okay, I'm done for today. Here are some exercises. The purpose of this meeting is for you to meet people, not to learn things. I mean, also a little bit, it's really to meet people, okay? So find somebody to work with, and then here are some treacherous exercises, okay? The first one is treacherous because it sounds easy, which is write down the rules for the unit type. Don't forget you have to write down everything, the declarative style, the equality rule, the bidirectional thing, everything. Okay, is it an extensionality rule? Is it a computation rule? Then you repeat the exercise for dependent sums, just because it's even more treacherous. Then, if you like to play with these things, there is an implementation. There are going to be 3 implementations. Tomorrow's implementation is already there, so you can have a look. And I do not recommend doing this with tomorrow's implementation, but maybe I will be impressed because it doesn't have any holes yet, no fixed arguments. Think about, like, at least have a plan. How would you derive the fact that this type theory is inconsistent? Frederick said it's inconsistent, Russell's paradox, la la la. But okay, do it. Okay. I suggest a Google search before you start. Okay, that's it for today. Thank you. It's late, but I think it's justified given the questions, and I'm very happy that you people were asking questions. This is actually useful. I was going to make a break in the middle for everybody, but you asked many questions. So tomorrow, I'll try to have a break. This is